Everyone, how you doing? I'm Mark Brown. I'm a program manager on the Azure Cosmos DB team. As I want to do when I do my sessions, I like to get a little quick selfie. So this room isn't really laid out to get everybody, so I'm gonna get you guys over there. So all right, everybody wave. Yay, hello. All right, there we go. Send that to my wife. All right, welcome to my talk, Build High-Performance Distributed Applications with Cosmos DB. And as I said, my name is Mark Brown, and I'm a PM on that team. So objectives for today's session, we're going to talk about distributed applications and building distributed applications. Really, the thing I want you guys to walk away with today is this third bullet, which is understanding the relationship between consistency, latency, and availability when you're building distributed applications. So why build distributed applications in the first place? Well, really there's two reasons. Availability for one. So what happens if, say, a region goes down in Azure, which never happens, right? Ever. What do you do if your application is no longer available because the network is down or storage is down or compute is down? The second reason you would build a distributed application is for latency. And what that means is just getting your data closer to your users, right? So the less distance that your packets have to travel from the user to wherever your data sits, the better the performance is going to be on your applications. So let me dive into some science here, and this is where I'm going to spend the bulk of this talk. And I'm going to go into these three concepts, and that's the consistency, latency, and availability. And each of these concepts is fundamentally tied to the other when you're building a distributed application. Now, when I'm talking about consistency, you may be thinking I'm talking about this. I'm not talking about this. Actually, in a distributed system, consistency relates to the uniformity of data on replicas or nodes that's separated by hundreds or even thousands of miles. Okay? So let's dive in. In 1998, computer scientists at UC Berkeley postulated what became known as the CAP theorem. And what CAP theorem says is, in a distributed system, I can only get two out of the following three things. I can get consistency, so I will always get the most recent write, or I get an error. I get availability. So every request will receive a response, even if it's not the latest data. Or I get partition tolerance. And what that means is that the system will continue to work, even if the network connectivity is lost between them. So to illustrate this, I have this little diagram here. So I have a network partition occurs within the system. I have two choices. I have to choose between availability within the system, or I have to choose for consistency within the system. By the way, these slides are all going to be up later. So, and I'll show you a GitHub repo where you got the slides and then a bunch of cool stuff. So let me illustrate that further. So here, I'm going to choose availability in this distributed system. So on the left, I've got a master node. And the right, I have a read replica. So choosing availability, I write 5 on the master, and then I read 5 on the replica. That works great when the network is there. But what happens in this system if I lose connectivity between those nodes and I try to write more data? I'm just going to get the 5 on the other side, right? So I'm choosing availability over consistency in this model. So I'm not going to get the most recent data within the system. Now, let's flip that over. Let's choose consistency. So in this system, I'm choosing consistency over availability in this system. So I write 5 on the left and I read 5 on the right. It works great when the network is there, but when I get a network partition, if I try to write more data into it, I get an error. I cannot maintain consistency within the system, so I cannot accept any more data. Make sense? Okay. Now, CAP theorem works good explaining what happens if a network partition occurs within the system, but it doesn't explain all the scenarios that govern distributed systems. And in 2010, CAP theorem was amended in what became known as PACLC theorem. And what PACLC theorem says is, in the case of a network partition in a distributed system, you have to choose between availability and consistency. But even when the system is still running normally, so absence of partitions, I still have another choice I have to make between latency and consistency. So what does that look like? Well, it looks like this. So on the left side, I've got CAP theorem, and I have a network partition in the system. And the two choices I have to make between availability and consistency. However, even if my network is working, I still have this choice of latency and consistency. So what does that look like? Well, let me illustrate this further. So in this system, I'm choosing consistency for my application. So same setup. I have a master node on the left and a read replica on the right. I'm going to write 5 over on the left master node. Now, in this system where I'm choosing consistency, What this means is that all the data in the system everywhere needs to be exactly the same. So I cannot do anything while that data is happening because I have to synchronously replicate it from the master node to all of the other nodes within the system. And then it has to act back. Okay? So that's the trade-off, is the amount of time it's going to take to do that. Now let's choose latency. So in this system, I don't care. I'm making a trade-off for consistency within the system. So what happens if I write data into it? I can just write as much data as I want into that node because I don't care about the consistency in there. I'm making a conscious trade-off between these two things. Okay? All right. Now let's get into some demos. This is the fun part, and you're going to like this. Let's go into read latency. So as we talked about latency, the lower the latency, the faster your applications are going to perform, and the better experience you're going to get for users. Oh yeah, hold on, let me set this up. So let's do a demo. I'm going to show you a demo of read latency with a single region Cosmos account and then a read from another region within Cosmos. So here's kind of the setup. I have a Cosmos account in EastUS2 and then kind of a fake web end. And then I have a VM, which I'm showing as kind of a web app, but this is basically my read client over in WestUS2. I'm then going to show you what happens if I create another Cosmos account and I have a write replica or replica over in EastUS2, and then I have another replica over in WestUS2. Okay, so I'm replicating the data over there. All right, let's flip to this. Where's my bill? Okay, so I'm going to run benchmark number 1, single region versus multi-region read latency. So I'm going to test 100 reads from this single master account. I've got my region is in EastUS2, and I'm reading it from WestUS2. And I'm getting somewhere in the order of 77 so milliseconds for that. So not too fast, about 80 milliseconds all up. Now let's test 100 reads, single master account, but now I've got a read replica from the write replica in WestUS2. Who thinks this is fast, by the way? Raise your hand. Yeah, oh, that just blasted right by. So 3 milliseconds. Okay? And there you can see. So average latency about 80 milliseconds. And then when I get the data close, it's 3 milliseconds. Lightning fast. Distributed data. Okay. Whoops. Back to slides. Okay. So that works great in a scenario where I'm just reading data. But applications don't just read data. They write data too, right? And you want to make the writes faster. So how did we solve that? Well, last year at Ignite, we announced a feature called Multi-Master. And what this does is it takes every replica in your system and makes it fully writable. The nice thing about this is now you get an SLA on your write latency for your data within Cosmos. So you're going to get a less than 10 millisecond write latency at P99, whereas before you wouldn't because you had to write that data across to another region. Also, 5 nines availability. Functionally, what you get is if every node in your system is fully writable, you get unlimited write scalability, right? So all I need to do is if I need to get more throughput because I've got more data, just spin up more regions, make them fully writable, and now I can kind of globally distribute all of my writes, right? So I'm adding more regions, not just more VMs. We've also got conflict resolution in there, and I'll show you that a little bit later. Adding multi-master is pretty simple. Just create an account, or for an existing account, you can just enable multi-master within your accounts there. Just add your regions. And then in your apps, even more simple. You don't really have to do anything with our new SDK v3. It'll automatically detect if your account is multi-master enabled. One thing you do need to do is within your application for each region is set the region that it's going to be running in so that it knows which replica to go talk to. Okay, so let's do some demos on this. So here I'm going to show write latency for a single write master versus a multi-master account. And here's my setup. In the same 2 regions again, I have a single master account in EastUS2 with a read replica in WestUS2. And then I'm going to show you the write latency for when I'm using multi-master. So now both nodes in both regions are now fully writable. All right, back to slides, or demo. Okay. So now I'm going to test 100 reads, single master account, read region, WestUS2 from WestUS2. And as we showed earlier, this is super fast, right? Because the data is right there. Now let's test 100 writes from West US 2 to my single master account, which is sitting in East US 2. And it's slow, right? I'm back to about the 80 millisecond, because that packet of data has got to travel 2,000 miles all the way across the US. Now I'll test 100 reads from a multi-master account. This, of course, is fast, right? Now I'm going to test a multi-master account in West US 2. Who thinks this is fast? Yep. Super fast, right? Way faster. You've got now multi-master. I'm writing my data locally within that region, and then Cosmos is going to replicate it to all the other nodes within the system. Okay, and there's my average latencies there. Okay, back to slides. Okay, so that's latency, right? And we showed how distributed systems can make improvements on latency by getting your data closer to where your users are going to be, either where they're going to read it from, or in the case of where they need to write it, using multi-master, and they can write their data locally to the region, and then we handle all the replication behind the scenes. Speaking of replication, one of the things you need to care about is consistency and understanding what levels of consistency you need within your application. Within Cosmos, we have 5 different levels of consistency, and I'll kind of go through each of these. We have strong consistency. What this means is that your data is synchronously replicated to all the other replicas within the account, right? Bounded staleness. So this is a relaxed level of consistency, and it's defined by either an amount of time or the number of updates that all the other replicas will lag behind the writes that happen within the system. Session level consistency is the most popular. It's our default within there, and I think for most use cases, it's the right level of consistency that you want. What this does is it provides a strong level of consistency within that region for the session that your application is running in. Session level consistency uses a session token in there, and that's kind of like an LSN that provides kind of the high water mark for the last piece of data that's written into the system, such that if you go and read that, passing in the session token, you will always get the most recent write that happened within that session or within that region. Anything outside of that session is going to get eventual level of consistency. So generally for applications, when you're operating on data, so if I'm a customer and I'm in West US and I'm hitting my application, which is deployed in West US, I'm likely going to want to use or look at that data. So session level consistency makes a lot of sense because you're going to read your own writes within Cosmos versus you're not going to be in West US and connecting to your application and your data there and then suddenly need to go and talk to East US. I mean, you wouldn't in terms of maybe if a failover happened, but the amount of time that would happen on the client side with the TTL for your DNS or traffic manager or whatever, that data is going to replicate already and be there. So session level consistency makes a lot of sense for most customers in most use cases because you want to read your own data that you wrote into the system. Consistent prefix is a more relaxed level of consistency, and what this does is it's more or less eventually consistent, but the updates happen in the same order in which they're written into the data store. And then eventual level of consistency, this is the weakest level of consistency, and as the name implies, data is consistent eventually. And there's no guarantees on what update you would see, so I could write 1, 2, 3, and then I could see 2, 3, 1 in other replicas within the account. You can change this level of consistency if you want within your application. So you can set it at the account level, and then in your application, you can relax it. And why you might want to do this is I might use a session level of consistency and then I want to run like a batch update or I want to ingest a whole ton of data. Drop my consistency level down to eventual. That's going to give me more throughput, jam in all my data, and then either kill the session or raise it back up again. What you can't do is you can't take a weaker level of consistency and then make it stronger. That you can't go that way, but you can go the other way where you relax it. So there's a direct relationship between latency and consistency, especially within a distributed system where you've got these nodes or replicas that are separated by hundreds or thousands of miles. And the further away they are, the more pronounced with the distance there. Now, most developers don't have to think or care about what the speed of light is, but in a distributed system, this actually comes into focus because you're dealing with such large distances between these things. Now, nothing goes faster than the speed of light, but since we don't really, networks or WANs don't really operate at that speed anyway, you've got things like network switches and routers and other kinds of stuff. Your data is going to travel at about 10 to 15% slower than what the speed of light is. And in a distributed system, it's kind of important to know what are the latencies between all the nodes, all the different applications that I've got in the regions they're in, so that you can kind of understand what that latency is going to be and deal with. In Cosmos, we'll allow you to use strong consistency within your account. But we limit you to 5,000 miles because the latency you're dealing with when you're replicating synchronously data over that great a distance is something that people may not understand. So if you really need strong consistency and you have replicas that are greater than 5,000 miles, just give us a call or send an email, and we'll ask you, do you really understand what you're doing here? And then if you say yes, or you make us think that you do, we'll go ahead and increase that for you. We're much nicer than that. Now, another trade-off you have to be aware of is there's a trade-off of consistency versus throughput. So within Cosmos, we do quorum reads and quorum writes. So a strong level of consistency, quorum write, is what we call a global majority, which means that all of your data needs to be replicated and committed in all of your replicas globally. Relaxed level of consistency on the write path, you're going to get a local majority. And what that means is on your replica set, and we have 4 copies of your data for every partition within your collections within Cosmos. We're going to write to 3 of those and commit it before we call it committed within your data there. So on the write path, you're going to get the local majority, and that's going to write to 3 of them there. On the read path, for a relaxed level of consistency, we just read from a single replica, right, because it's a relaxed level of consistency. For strong and bounded staleness, we read from 2 replicas. So what happens here is because you read from 2 replicas, this is 2 computers, it's 2 RU. It's twice the cost. Or the other way of looking at it is that you're going to get half the throughput on your read path when you use a stronger level of consistency like bounded staleness or strong consistency within there. Another thing I want to call out too is in a distributed system, if you choose consistency, you lose one of those nodes, you're no longer able to write data anywhere. In Cosmos, we have what's called a dynamic read quorum. So if you have an account set up with 3 or more regions in there and you're using strong consistency and one of those regions becomes unavailable, you can still write your data and commit it. So we'll dynamically drop the lease for that region until the region comes back, but we'll continue committing data into the other regions. When the region comes back, we'll go and then we'll backfill that data so everything is consistent again. So let's do some more demos. So this is 2 sets of demos here. I'm going to show you the trade-offs between consistency and latency, and then I'm going to show you another set of demos that shows you the trade-off between consistency versus throughput. So here's my setup. I have an account set up in WestUS 2, and I'm going to write a bunch of data into this, and then I'm going to replicate it 1,000 miles to Central US region. It's about 1,000 miles away. I'll then show you what the latency is when I have an account set up with strong consistency in those same 2 regions, so 1,000 miles away. And then to kind of show you what happens when the speed of light here, I'm going to double the distance for this account with strong consistency and then show you what the latency is going to be on it. And then on the consistency versus throughput, what I'll show you is the cost of reads, the RUs, for doing 100 reads using eventual consistency versus strong consistency. Demo. Okay. Consistency versus latency. So I'm going to test 100 writes. This account was with eventual consistency in WestUS 2, and I'm replicating it to Central US. Who thinks this is fast? Who thinks this is slow? Nobody. Okay. It's fast, right? Because I'm using eventual consistency here. I don't care about consistency within this system, okay? I'm going to get the highest throughput on that. All right, let's test 100 writes with an account with strong consistency, WestUS, replicating 1,000 miles to Central US. Who thinks this is fast? No. Who thinks this is slow? All right. You guys are catching on. Slow, right? So every piece of data I write, I have to replicate and commit 1,000 miles away and then ACK it back. All right, let's test 100 writes, strong consistency in WestUS. And I'm going to replicate it to East US 2, so it's more than double the distance. And double the distance, double the latency. Oh, what's going on with my Wi-Fi here? There it goes. Right, direct one-to-one relationship. So the further distance you go, you just basically are just increasing it. All right, now let's test throughput. So I'm going to test 100 reads with eventual consistency, and I'm going to measure the throughput usage on it. And that's just 1 RU, because I'm just hitting a single replica within my replica set. Now let's test strong consistency and then measure the throughput. And here you can see it's 2 RU, because I had to read from 2 different replicas. And that's, in fact, how we maintain consistency within your account. because we'll check the LSNs between there, and if they're matching, then we know the data is consistent. You have strong consistency within the replica. If they don't match, we're going to pick the one with the higher LSN, because as you saw earlier, we only write to 3. So there's that small microsecond window there where you may not be completely consistent within the entire replica set. So if we check 2 of them and one of them's higher, then we're going to say, well, that's the more recent write. And that's the one we're going to return. OK? And back to slides. How am I doing on time? I'm doing good. OK, we've talked about latency. We've talked about consistency. Now the third topic is let's talk about availability. So if you've built anything in Azure or done any kind of distributed systems or architecture or whiteboarding, you probably this would look familiar to you, right? So I've got just kind of my generalized application here, and I'm either connecting to it with a device or a browser or a mobile phone, and it's going over this cloud thing that's the internet. And then we're using DNS load balancer like Traffic Manager because I want to load balance geographically into each different region. And I'm going to do that because I want to get the latency lower for my clients that are going to connect to it, right? So I'm going to say, connect to the region that's closest to where this customer or this client is coming from. So I need to have, in a system where I'm trying to build availability, I need to build availability in multiple ways. I need to do it at a regional level, so I should be deploying my application into multiple different regions, because what if a region goes down? What if a natural disaster happens? I want my application to be available and still working. Within region, I also need to build resiliency in. So within my web tier, I'm going to deploy multiple VMs or app service instances or something in there. And then in the middle tier, I'll do a similar thing. And then I'll load balance across those address pools within there so that I'm distributing that load within there. On the data side, you could use Cosmos DB, right? So we've got 4 sets of data. So we've got in-region resiliency for your data because we have 4 copies of your data. And we only need 3 of them at any time to allow you to continue to operate and to write data to that. In fact, this happens quite frequently is we'll do updates on the compute for each of the partitions within there. So we'll drop one out and put another one in, and you'll never know what happened because you're fine. You just keep writing, right? So that's how we kind of maintain, it's kind of a self-healing, if you will, with the service in the back end. So, and then of course, so we've got resiliency at the regional level, and then of course, because we're globally distributed and you've got replicas in each region there, you're protected at a regional level well. So this is a pattern you'd want to follow if you want to build highly available applications in Azure using this pattern here where I'm deploying into multiple regions and I have in-region resiliency, and then I'm using Cosmos at the back end where I've got both that in-region resiliency as well as resiliency for regional failures that happen. So who knows what RPO is? All right, who wants to tell me? Right. And what's that mean?
Basically, how long it's acceptable to be losing data.
Right. And what's RTO? Who knows what that is? Right. What's that mean?
How long can you go with
You guys are awesome. Well, it's actually how long can you be down, right? So RPO, how much data can I lose? And RTO, how long can I be down for, right? And they're both a function of time, right? And I like this graph here because it helps visualize what do both these things mean within my application. If you're building a distributed application, you absolutely, well, any application, you really care about these things, right? And customers will say, well, I have an RPO of 0, or I have an RTO of 0, or in some cases they'll say, I need RTO 0 and RPO 0, and I say, that's crazy, you can't do that. And I'll tell you why in a minute. Within Cosmos, we publish our RPO and RTO. So customers that come to me and they say, I have extreme uptime requirements. Right, okay, how many regions are you deployed in? Just 1. I'm like, no, that's not right. You can't do that because regions go down. You can't have any kind of 9s with your availability if you run in one region. And then I show them this thing and I'm like, look, our published RTO for an account that's just in a single region is, we call it just something less than a week. Now, regions don't fall down for an entire week, but just to be on the safe side, this is what we publish as an RTO for an account that's just within a single region. Your RPO is going to be 240 minutes or 4 hours, and that's the default interval for when we take snapshot backups of your account within Cosmos DB. Now, you can change that and reduce that. You can also, by the way, we only keep 2 copies of that. You could also call support and ask them, give me a longer retention period. So we generally recommend customers get 100 hours of backups within there because that'll cover like a long weekend. So if someone goes in there and borks all your data on Friday afternoon and it's a holiday weekend, you can come in Tuesday and still get a snapshot backup of your data in there. So go for 4 hours. 4 hours works for you, great, but definitely go and get 100 hours for your backup. So back to this. Single region, ridiculous. You don't do that if you want to be highly available, right? Because regional failures happen. Single master account, relaxed level of consistency, RPO 15 minutes, okay? And RTO of 15 minutes. Your RPO of 15 minutes for that relaxed level of consistency is functionally the amount of time it would take to replicate or to ensure your data is replicated into every other region globally within Cosmos. Now, in practical terms, that RPO is frankly much, much less. It could be milliseconds depending on how much load you're putting on your application. Your consistency is going to be driven by how many RUs are not being used or unused RUs or throughput within your database, because we replicate data based upon the amount of available RUs you have available within your account or within the container. So this could be far, far less. But for that relaxed level of consistency, we bound it by 15 minutes within there. Your RTO of 15 minutes, what that functionally is if a regional failure happens and you're in auto failover mode, that's the amount of time it takes Cosmos to fail you from your, or to take and promote one of your read replicas to be a full write master. Okay, so that's your max downtime is going to be that. Customers will typically use a manual failover mode and then write a little agent that's just pinging the endpoints and just seeing if they're healthy. And if they detect them they're not healthy, you just trigger an automatic failover. And generally, failovers happen in less than 5 minutes, so, and even sometimes quicker. So you can get an RTO that's pretty low in that sense where you're just down for a few minutes. Bounded staleness, as I said, this is bound by time and update. So it's a function of K and T, and that's 5 minutes or 100,000 updates for a multi-region deployment. Strong RPO of 0, of course, right? Why? Because I've committed it into another region or all the other regions, so I got no data loss whatsoever. Same RTO in terms of being able to fail over. Where things get really awesome is with multi-master, right? So you're going to get the same RPOs that you got for a single master account, but you're getting an RTO of 0. And the reason why is because in our SDK, we actually detect if a region becomes unavailable, and then we'll retry the request in the next region that you have configured in your account, right? It's magic. RTO 0. So remember earlier when I was saying you have this trade-off between availability and consistency. If I'm RPO 0, what am I optimizing for in terms of CAP theorem? Consistency, right? If I'm RPO 0, I have to be consistent. I have to optimize for consistency. So knowing what my RPO is translates directly into what consistency level I should be using within Cosmos, right? It's one of the factors that come into it. If I have an RTO of 0, if I can never go down, what am I optimizing for? Yeah, right? You cannot have both. It is physically impossible to have an RPO 0 and an RTO of 0. So if someone ever says that to you, just tell them, Mark Brown says you're nuts. Okay? All right, let's move on to conflicts. I got 16 minutes. So when you've got a system where I can write data from any different node, you could have the potential for conflicts to get introduced to the system. Cosmos provides 3 different ways you can do conflict management within there. Our default is to do last writer wins, which as the name implies, the last write that gets in there, or the one with the higher value for its timestamp, is the one that's going to be win. It's the one that's going to win. We also have a custom merge stored procedure, where you write a stored procedure in Cosmos, which is JavaScript, and then you can handle the merge conflict within there. And then the last one is we don't do any conflict resolution, and then we just write it to a conflict feed, and then you read the data, and then you process it, and then you figure out how you want to do that. So for last writer wins, this is the default, and functionally what it's doing is it's using the timestamp for the records that get written into Cosmos, and then when it's merged, just looking for the higher value. For our SQL API, you can actually just use a custom numeric property or value within there, and then we'll take the higher value there. So here I've got a record with Scott and then Satya, and who's the winner there? Oh, so Satya wins, right, because he's got the higher value. And then you just set the path for that in the portal, or you can do this in ARM or PowerShell or whatever, but you just set the path for that, and then we'll use that value to merge that for you. And that custom merge procedure, as I said, this is JavaScript, right? And then it has a special signature in there that looks like this thing here that you can kind of see. And so you just register this as a regular stored procedure within there. It's only, like every stored procedure in Cosmos, it's scoped to a container and then also bounded by a partition key value. Okay, so you can use any other data within that partition to help resolve the conflict that happens within there, but you're bound by those things within there. Also, of course, because it's a stored procedure, only for SQL API only, and this is executed as part of the commit within there. So you do not, just like with last writer wins and with this, you do not see an error or notification or anything that any kind of conflict happened. This is all silently managed for you. If it throws an error inside the stored procedure, we will then write that to the conflict feed. So if you're using custom stored procedures, you're going to want to write a little agent to monitor this thing. Unlike change feed, you have to actually write an app and then just pull our conflict feed and then see if there's any conflicts in there and then go and process them. And this is kind of how you would write code to kind of manage your conflicts within there. So you just kind of for each through the conflict feed, look for conflicts within there. And then you can say if it's a create operation, handle it that way, or if it's an update, handle it that way. You could do a delete if you want, but I don't know why you would want to go and merge a conflict on a delete. If it's deleted, right? And then after you're done processing it, just go and delete the conflict off the conflict feed within there. This is great. It's more complicated, but because it's just its own app, you can basically or functionally use anything you want to help merge your data, even calling other third services or anything you want or another database. So the more power with this, but it's more complicated to do. All right, let's do some demos. You see that? Okay. All right, so I'm going to generate insert conflicts. Oh, let me show you. I don't have it up here. All right, what I've got is I've got a multi-master account. I've got a region in West US 2, East US 2, and then I've got another one in North Europe. I'm going to go and insert data into all three of those regions simultaneously, and I'm going to try to generate an insert conflict in here. And I'm using max user-defined wins, and hold on just a sec. What I'm missing here is, let me get this up. I want to be able to see our data when it gets written. This is it. Yep. Sorry, I should have had this up before. Okay, so I've got three containers in here. This one is using last writer wins. So if I go and I look in here, I have a user-defined ID, custom resolver property. So anything I write in here, the higher value for that property is the one that's going to win in here. I then have another one that's using a stored procedure that I've defined in here. And what this one is doing is it's functionally using the lower value of that. So I'm basically using the same type of data, but I'm going to use the lowest value in that. And then I have a final one here. This one doesn't have anything set up in here, and I'll show you the conflicts that happen within there. Okay, so let's go back to demo. Okay, so I'm going to generate insert conflicts on this container using last writer wins policy. The maximum user-defined ID will win. And retry. Okay, so Haley Doherty, user-defined ID 576 that was written in the East US 2. That should be my winner. Wrong one. And there it is, 576. Right? So using that property there, resolve that conflict that happened within there. Okay. Now let's generate insert conflicts with user-defined procedure. So this one, the minimum value is the one that's going to be the winner. Okay, so Colt Schulist, the user-defined ID 163, also in East US 2. Let's try that one. And there it is, 163. There's my winner. Cool? All right. By the way, it's very difficult to generate conflicts, I just want to tell you. Now I'm going to generate update conflicts on this container with no policy at all. So it's going to write to the conflict feed. So what I'm going to do is I'm going to write a piece of data, and then I'm going to let it replicate. That was pretty quick, by the way. And now I'm going to do simultaneous update in 3 different regions, and that generated a conflict. So let's go and see what happened. None. And let's look at conflicts. Huh, that didn't do a conflict in there. Well, there's my data, but no conflict showed up. That's strange. Okay, well, that part bombed. All right, moving back. Okay, that's conflict resolution. I got 9 minutes. Let's talk about custom synchronization. So I showed you earlier how much latency you get when you have to replicate data using strong consistency, right? Because it's synchronous. And it has to commit into all the other different regions. You can actually pull a kind of a special trick using what's called a custom synchronization. And the way that works is you use a more relaxed level of consistency across the entire account and all the other replicas you have within there. And then you create functionally region pairs between 2 regions that are pretty close to each other. And then you create a strong level of consistency in there using the session token. I write data into one region, and then I read it out using another connection client, a Cosmos client, and I flow the session token from one to the other. So let me show you a demo of how that works. So in this one here, I'm going to test 100 writes, strong consistency in West US 2 replicated to East US 2 in North Europe. And you can see that's pretty slow. About 120 milliseconds. Yeah, 117 on average there. All right, now I'm going to test 100 writes. I'm using session level consistency. But what I'm doing is I'm going to write into my account in West US 2, and then I'm going to read it immediately from West US. So I'm going to force a sync. And I'm going to use the session token to do it. Because remember, that session token is just an LSN. So what it does is that if it's there, great, it pulls it back. If not, it goes and pulls it and gets it. And there, much better. So I get about 60 millisecond latency. Cool, huh? Thinking kind of cheating Mother Nature there a little bit, right? But I'm forcing that data. I'm now durable in 2+ regions, right? So I'm going to get a better RPO. But I did not have to trade off all the, I didn't have to take the hit on the latency to replicate to all of my other accounts. So this is an option where you can kind of get a better RPO and not take such a hit on latency. If you want to see how I did that, let me show you something. So here, let me just get out of that. Kill this. And where are you? Oh, sorry, it's in here. There you are, custom sync. Okay, so I've got a sync client and container here. And then here I'm doing a write, create item async in here. And then with my response object, I'm going to take the response object, and out of the header, I'm going to grab the session token from that, and I'm going to do a read item async immediately before I come back from making this call. So that's how you would implement it at your in the code if you were trying to do something like this. It just flows the session token across there. Okay. Okay. So session takeaways. I hope you got something out of this talk. I hope it was fun watching those demos. I liked showing kind of actually what happens in the real world when you're building a distributed system and understanding those trade-offs that you have to make between consistency and availability and consistency and latency within systems of this type. All the demos you saw, including the deck for this presentation, is up on GitHub, right? I can show you that. And then there's some great articles on our docs that explain how things like global distribution works and how CAP theorem and PACLC, they're all great because I wrote all of them. So you can go and check them out. And then we talk about the consistency levels within there, understanding the trade-offs that happen within there, and then also designing for high availability within the system. So that's it for my part of the talk. If you guys have any questions, I'll take them. Yeah, question here.
So the pre-con Sunday, right? There was supposed to be a session on the server side, just like triggers and store parts. I didn't see it in the schedule.
I'm not sure. So the question is that our pre-con, did we had a thing on stored procedures and on a session on the server side stuff? Yeah, I don't know. I checked our schedule. Or go to our booth, we could tell you. Yeah, question here?
Who have you talked to for consulting this kind of stuff? Is it straight to the product group or is their experience with the
Yeah, you could come see me and I can kind of help you find a partner that can do this kind of work and help you design. Yeah, it's not a huge partner ecosystem, but it's definitely growing and there's some great partners out there now. Yep. Yeah, another question. Yeah, so that's in the portal where you set that. So let me show you. So you're going to set your consistency level here within the portal on the default consistency. It's for you set consistency for the account. Yep. Yeah, another question. Oh, you mean in the Data Explorer? Yeah, all that stuff was all at 400 RU. It's all minimum RU.
Well, no, I mean, but the tricks with regard to reading when you go on the Azure, your RUs or
Correct. Yeah, that's a good piece of feedback. So, another question. Yeah, if you're using defaults, you're getting 8 hours of backups. You're getting 2 4-hour backups. So go call support and say, hey, I'd like a 100-hour retention period, and we'll do that for you. Simple as that. What's that? No cost. No cost. So question?
So what should I look for in the other areas of my solution for availability, not just the Cosmos? I can make this like, say, highly available solution, but then like, say, for my application or that, for example, what should I look to that layer so that it goes with the Cosmos DB available? I can't have that in like less available.
Right, so the question is, how do I make my app more available? Well, so if you go back to that diagram I had, the way you do that is multiple instances of your application that are load balanced within an app pool, right? Because if any VM falls down, that's fine, it gets dropped out of the pool, and then the requests just continue to get spread among the other VMs. And then hopefully you've got some kind of self-healing thing going on there that detects, hey, one of my VMs fell down, go spin up another one, join it into the pool, and then go ahead and load balance over all of them again.
SDK you were mentioning, that's basically you need to code or it's smart enough to find the available Cosmos DB.
Yes, so within Cosmos, when you set your application region within there, it knows which local regional replica to talk to. So it'll talk to that, and then if it fails over in a multi-master configuration, we actually inside the client know what other regions you're working on, and then we have a map of basically the latency between all the other regions. So we'll say, just go retry on the next closest region within your account. And then when that region comes back, we'll detect that and then bring it back in. So it'll go back to default. So if you don't have to do anything. But typically, when a region goes down, it's not us that's actually the problem. We don't take a dependency on anything in Azure other than networking. Usually it's storage or AD or who knows, something else goes down. We've survived a lot of regional outages, and we're still serving requests on our data plane. So if the application's not impacted by whatever's out, customers will typically still remain available because we don't really take a dependency on anything in Azure, just the networking, of course, because without the network, what are you? And in fact, a lot of services in Azure now take a dependency on us because of our availability and our ability to kind of survive service outages. Question?
How do you help people choose between the new Azure SQL Data Store Hyperscale and Cosmos?
Yeah, I guess. I mean, I can't really say much about hyperscale. I know they kind of built it to kind of get past kind of their, 4 terabyte limit in there. Right, and how'd they do that? They partitioned it, right? Well, we're already horizontally partitioned, so we never had that problem to begin with. You could have a megabyte or a petabyte of data inside Cosmos, and you're still going to get less than 10 millisecond latency response times for that data. So hyperscale is kind of a fix to something that's just kind of an innate limitation to relational databases, which is you can only scale up so far. You eventually have to scale out. We obviously feel this model is better to begin with. Start with a horizontally partitioned model because your scale is unlimited functionally. We also have latency guarantees. I don't think hyperscale has a latency guarantee either, right? So we have an SLA on availability, so that's 5 nines when you're in multiple regions. And then also a latency SLA of less than 10 milliseconds at the 99th percentile. And as you saw there, I'm getting read latencies of 3 or 4 milliseconds, right, on average. So much faster. Yeah, question?
Less than 10 seconds for eventual consistency too?
I'm sorry?
So you said less than 10%. Does it apply for eventual consistency too?
Less than 10%. What?
So latency.
So latency on a read or a write, less than 10 milliseconds, right? So a point read or an insert, less than 10 milliseconds at the 99th percentile. It's nothing to do with, and that does nothing to do with the consistency level. Although I will say this, and that would be on the read path, fine. On strong consistency, there's no latency on that because you have to replicate the stuff, right? So that doesn't apply to strong, your write latency at less than 10 milliseconds doesn't apply to strong consistency because you have to replicate the data, right? But for all other consistency levels, you're fine. On the read path, you get less 10 millisecond latency on everything. Doesn't matter the consistency level. So, yeah, another question? Yep. Yeah, in fact, I originally wrote these demos using the V2 SDK, and I just updated them to V3 like a couple of weeks ago. So, yeah, this is really easy to set up and use, by the way. So I'll show you in here in GitHub. I walked through all the benchmarks I showed in here, and then this thing is just a basically one-click button deploy, and then just put some strings in there to fill out your information. It'll provision all the accounts. It won't cost you anything to just run this. You do need a VM to run that project in, and that should be in WestUS 2, which is where I centered this whole set of demos. And then when you run initialize, it'll create a whole bunch of containers, but it does it all at 400 RU. Okay, so go ahead and run it initialize, and then when you're done, run the cleanup on there because you don't want to leave those things running, right? So I'm using minimum RUs, but it's just like don't go provision a massive VM and then leave it on and forget about it, right? Go shut the thing down or deallocate it. So same idea. Yeah, question?
So my app servers, let's say my app servers are in UK Azure, and my Cosmos DB is like multi-master Cosmos DB. So from the app perspective, how my app should redirect to, let's say I have a customer from UK connecting to US, needs to talk to US Cosmos DB because my app server and Cosmos DB same region, right? So how can we map these like app server with Cosmos?
So if you're in multi-region, you should use Traffic Manager, right? Which is going to basically know which is the closest region to direct your client to. So if you're in UK South and East US and your customer's in UK or in London, Traffic Manager will direct them to the UK South region for serving up the request.
Okay, so can I have the same Cosmos server on the UK's South?
Yeah, so you can replicate. We're a Ring 0 service, so we're in every single region in Azure. In fact, you cannot stand up a region in Azure without Cosmos because everybody takes a dependency on us. Yeah, question?
So I was wondering which of these levers we use if we're doing PaaS solutions with Azure Functions using like Cosmos binding stuff. We got choices.
not for that. I mean, you would configure the consistency level within the account for Cosmos. We do have functions bindings for that. So in fact, that's very, everybody heard of change feed? If you haven't heard of change feed, go Google change feed, or excuse me, Bing it, change feed. So data that goes through change feed is eventually consistent, right? Because there's no consistency guarantee. You're reading it functionally out of Cosmos, doing something with it, and then either writing it to another container or, I don't care, you could do anything you want to with it. You could go shove it into an event hub or whatever. But data, once it's committed, is in there. Data you do anything else outside of that is eventually consistent. Now, your consistency is going to be small, but at that point, it's already committed, so you're already consistent. You can assume the data that comes into change feed is it's committed. Yep.
A follow-up question. So actually, my application is distributed across the world. I have customers from India, Japan, China, and UK, and the US. So when I deploy my application to different regions, I want to have my application distributed across the different regions.
Yes.
I know. But how a user, like how my app know, okay, I need to talk to Cosmos DB in US, Cosmos DB in Japan, based on the request.
Right, so you're going to set that application region in your connection policy and set it to the region that application is deployed into. So that's just going to be driven from a config. So each deployment, each region, and you can set this up in DevOps pretty simply, but if I'm going into India South or into East Asia or into West US, each deployment that goes to each of those regions should have, knows which region it's going into. Just set that value in your connection policy, read it out of your app settings JSON, and then you're fine.
So if one of DB down in Japan, let's say,
Yep.
so will Cosmos will be able to redirect the traffic from Japan to US?
Correct.
Any,
We will redirect your traffic. If we detect, in multi-master, if we detect the region's not responding, we will automatically retry that request in the next closest region.
so from the app side, we don't need to do
You don't need anything. But here's the thing, right? So typically, if services are down, it's your app is also probably down. So the other thing to configure is the TTL for Traffic Manager, because it also needs to fail over requests coming from the client to another region.
Sometimes I mean, with the DB that right now I'm working, sometimes the DB might go down because of the, it's not actually DB goes down. There's a possibility of conflict management in the DB, right? When they do a replica, I'm using MariaDB.
Okay.
So when it does like conflict management, so at the time, even the app sends a request, DB won't respond back. So we have to do a retry to insert or get the transaction. So do we need to do some kind of thing for Cosmos or like?
You need to do anything. I mean, just use the conflict resolution like I showed you there, and yeah, you're fine. So it's pretty bulletproof. Hello.
I have two apps. The first one writes data. The second one absolutely needs to see the latest data.
Mm-hmm.
We use strong consistency right now for that.
Are they in two regions, these apps?
Same region.
Yeah, if you run in single region, strong consistency makes no sense. Or you don't need it. Because you're strongly, the consistency applies to replicas in different regions.
How can we guarantee that second?
In fact, you're actually getting half the throughput you should be getting because you're paying 2 RU for every read.
I agree. It seems like a bad idea.
Yeah, you don't need it.
So how do we guarantee that second app?
Yeah, use session level consistency and then take the session token and then flow it over to the other app. Yeah.
Does the session token live for the duration of the connection?
Yes.
Okay. Very good. So we just write some data that first time, grab the session token, move it to the other process.
Yep.
Got it.
I'm out of time, I think. So